Hi everyone, welcome back. In this section we're going to look at the spherical coordinate system and how to set up triple integrals in these new coordinates. First, let's look at a motivating example. We want to find the centroid of a homogeneous solid hemisphere of radius 1. So homogeneous just means it's constant density throughout, so we might as well assume density 1 just for simplicity. So homogeneous means constant density. And let's just say the density is equal to 1 for simplicity. So it's a hemisphere of radius 1. So let's get a look at what this region looks like. So we're looking at something like this. And so there's our hemisphere. We can write it as x squared plus y squared plus z squared equals 1. That's really the equation of the whole sphere. So if we're interested in just that upper hemisphere, we can solve for z. It's the positive square root of 1 minus x squared minus y squared. We've also got a footprint. So if we're thinking about a z first integral, we've got a footprint. So we'll say z first integral. And what's our corresponding footprint? Or our projection of this region down into the xy plane. So it'll be a circular disk of radius 1. So this would be given by the equation x squared plus y squared is equal to 1. Now in order to find the centroid, we would need to evaluate each of these three integrals, but first we'd have to evaluate the mass integral. So how would we get the mass integral? Well, we would say m is equal to the integral of the density function. In this case, we're thinking density is 1 dv. We'd integrate over that region. I'll call it h for hemisphere. So that's the integral we'd want to evaluate, which means we need to set it up. We need to set up integration over this region. If we were to do rectangular coordinates, or our usual Cartesian coordinates, then what would our mass integral look like? Well, we'd have that mass is equal to, since we're doing a z first integral, the outer twomost integrals is going to sweep over that circular disk, but our innermost integral is going to be our z values, which go from 0 up to the square root of 1 minus x squared minus y squared. The density we're just assuming to be 1, so this would be dz. And then we want to integrate over the disk. In order to do that, we could do, say, something like the upper hemisphere, or the upper semicircle, I should say, is y is equal to square root of 1 minus x squared, whereas the lower one is y is equal to negative the square root of 1 minus x squared. So if I think about integrating along the y direction next, I would be integrating from negative root 1 minus x squared all the way up to the square root of 1 minus x squared. So that would be our dy integral next. And then we'd have our dx integral last, and that would go from negative 1 to 1. So there would be our integral if we were to set it up using rectangular coordinates. But since we're integrating over a rectangular disk, very natural reaction is to say, well, let's use polar coordinates for that. So in other words, we're going to use cylindrical coordinates over the whole thing. So if we were to do this same thing, setting it up with cylindrical coordinates, our integral would be, we'd integral over the disk, and then our z value, and then cylindrical coordinates would be r, and then let's do it dz, dr, d theta. So z ranges over 0 all the way up to the hemisphere, but in terms of polar coordinates, or cylindrical coordinates, we have z is equal to 1 minus r squared. And how about our region in the plane? Well, in the plane, this would be the polar coordinates, part of it. And so that would be described by r goes from 0 out to 1, and theta goes from 0 to 2 pi. So z goes from 0 up to 1 minus r squared, r goes from 0 to 1, theta goes from 0 to 2 pi, and so there's our integral setup in cylindrical coordinates. The nice thing about using cylindrical coordinates is now two of our integrals, the outermost integrals, have constant lower and upper limits of integration. So it's like we do the first integral with respect to z, and then we integrate over a polar box, a polar rectangle, for the outer two integrals. This begs the question, we started with an original triple integral where we only had one of the integrals that had constant lower and upper limits of integration, the other ones involved variables. We switched to a new coordinate system where two of our integrals now had constant lower and upper limits of integration, and then variables in the third one. Can we come up with a coordinate system where all three of the integrals have constant lower and upper limits of integration, and the only place the variables appear then are in the integrand themselves? That means, can we convert this to a new coordinate system where the integral is over a rectangular box in that coordinate system? That's where spherical coordinates are going to come into play. So the question we want to ask is, can we find a coordinate system where the integral is over a rectangular box, and I'll put rectangular in quotes, or rectangular box in quotes, because this is a rectangular box in that coordinates. Just like the circular disk, that's not a rectangular box in rectangular coordinates, but the circular disk we can think of as it's a rectangular box in polar coordinates. Theta is between two constants, r is between two constants. And the answer is, can we find a coordinate system? Yes, we can. It's known as the spherical coordinate system. So spherical coordinates are defined as follows. The idea is, for any point in space, any three-dimensional space, we can describe it using three values. Originally, we used the three values x, y, and z, and those are just distances from coordinate planes. Or we can use cylindrical coordinates, where we use r, theta, and z values. In spherical coordinates, we use what are known as rho, theta, and phi values. And the picture summarizes what these values capture. So rho is just the distance from the point to the origin. So here we're thinking of this as our point. And so the rho value is just the length of this line segment out to that point. It's the length of the line segment OP. So that's rho. Now, that's our first component describing the position of this point. What's our next one? Well, the next one is the angle that the point O, or that the line segment OP makes with the z-axis. So that's this angle here. How much did we have to drop down? Say we got the z-axis, then we got to drop it down until we hit that point. What was the angle I moved that line segment through? That's the phi value. Sort of this unfolding from the z-axis, and where do I stop before I hit the point? That's our phi value, and it's shown in the diagram down here. So phi. And then the last component we have is, if we take that point and we project it down into the plane, then that point is now a point in the xy plane, and we can use the theta value, same theta value we have from polar coordinates. We use the theta value as the third component. You can think of this theta value as, once I have this point, I can draw a vertical plane. Maybe I'll just shade it in like this. I can draw a vertical plane through that point, and theta is the angle that this plane has sort of been, like a page of a book, how much it's been opened up from the xz plane. So what the angle between this page and the xz plane is, that's our theta angle. So we'll get rid of these line segments. So those are our values. Now, how do they relate to our rectangular coordinates? Well, they relate as follows. So let's look at this triangle first, this right triangle, the OP and then the Q triangle. So this is a right triangle as indicated by that little right angle at the point Q. And since this is a right triangle and I know the hypotenuse, its value rho, and I have this angle between the hypotenuse and one of the sides, which is phi, then I can work out the values of these other sides. This would be rho cos phi, whereas this one is rho sine phi. So that distance there is rho sine phi, whereas the z value of the point in this case is rho cos phi. So we can even write z is equal to that. So that tells me already I have a relationship between the rectangular coordinates and the spherical coordinates. Z is equal to rho cos phi. What else do we have? Well, that rho sine phi, that is actually just the length of this line segment down in the plane below. And that's just the distance the point is to the origin. Or rho sine phi, you can think of, it's the distance from the point up the original point to the z-axis. So that's our r value if we want to think about it in terms of polar coordinates. So if that's our r value and we have our theta value, then what is y? Y is equal to r sine theta, but r is rho sine phi, and then that's times sine theta. Whereas what is x? X is equal to r cos theta, and r is rho sine phi, cos theta, and so that's equal to our x value. Maybe I'll just cover up the x and just say that's equal to x. So that's these other two relationships. X is rho sine phi cos theta, y is rho sine phi sine theta. What about going in the opposite direction? So that was going from spherical coordinates to rectangular coordinates. What about if we wanted to go the other direction? How would we go from rectangular coordinates, if we had the x, y, and z values? How would we go from those to the spherical coordinates? The rho, the theta, and the phi values. Well, rho, the square of rho, is x squared plus y squared plus z squared. So that's one relationship that says if we know the x, y, z value, we can find the rho value. We also have that from our equation z is equal to rho cos phi, we have that cos phi is equal to z over rho, but we just found out that rho is the square root of x squared plus y squared plus z squared. So there's a relationship that gives us from our x, y, z value what our phi value is. And lastly, we have the same relationship for theta and as related to y and x. So tan theta is y over x. So those three equations give us the rho, phi, and theta values from the x, y, z values. Let's get a little bit of practice in working with converting between these different representations. So we're going to find the rectangular coordinates of the point having spherical coordinates 2 pi by 4 pi by 4. So right now we have rho theta phi is 2 pi by 4 pi by 4. X is equal to rho sine phi cos theta. Y is equal to rho sine phi sine theta, and z is equal to rho cos phi. And so this is 2 sine pi by 4 cos pi by 4, or in other words 2 times 1 over root 2 times 1 over root 2, which is 2 times a half, which is 1. Similarly here we get 2 sine pi by 4 times another sine pi by 4, which is 2 times 1 over root 2, 1 over root 2, which again is 1. And lastly we get 2 cos of phi, which is cos of pi by 4. And so that's 2 times 1 over root 2, or in other words, root 2. So therefore, the rectangular coordinates of that point is 1, 1, root 2. How about going in the other direction? Let's find the spherical coordinates of the point with rectangular coordinates x, y, z is equal to -1, 1, 1. So the first thing we note is that rho squared is equal to x squared plus y squared plus z squared. And that is equal to 3. So we have that rho is equal to root 3. Next we have that tan theta is equal to y over x. Y over x, that's 1 over -1, so that's -1. And so what is tan theta? Well, we can get a picture for this. Nice to know which quadrant we're in. So we're at -1, 1 in the y, so we're over here, and then we're up along the z-axis 1 unit. So we're here. The angle theta we're looking for is this angle here. So that's theta. So in terms of the plane, theta lives in the quadrant 2 of that plane. And so we know then that theta has a reference angle of pi by 4, and it's actually a value of 3 pi by 4. And so what about our phi value? Well, we have cos of phi is equal to z over rho. Z is 1, rho is root 3, so that tells us that phi is equal to cos inverse 1 over root 3. And so there we go. We found our rho, theta, and phi values. It's root 3, 3 pi by 4, and cos inverse of 1 over root 3. Okay, so that's how we can convert back and forth between rectangular coordinates and spherical coordinates. Next on our list is describing surfaces, and then regions using inequalities. So this first example asks us to find the cylindrical coordinates equation for the sphere. So we've got a sphere, x squared plus y squared plus z squared is equal to a squared. What is it in terms of cylindrical coordinates? Well, remember, cylindrical coordinates, we had x is r cos theta and y is r sine theta. Basically, it was z value is the same, but it's polar in the plane. So x squared plus y squared, that becomes an r squared. Z squared remains the same, and that's equal to a squared. So there is our description of that sphere using cylindrical coordinates. Let's now describe the same sphere, but using spherical coordinates. So again, we've got x squared plus y squared plus z squared is equal to a squared. In this case, we're going to use our x is equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. And x squared plus y squared plus z squared, that's equal to rho squared. So this becomes rho squared is equal to a squared, or in other words, we can write it as rho is equal to a. So that tells us that we can describe the sphere in spherical coordinates by just the set of all points whose rho value is a. Rho value is a constant, whose distance from the origin is a. So this is a sphere in spherical coordinates. And that's very nice because it says that in using spherical coordinates, spheres are very easy to describe. They're just one of the variables equal to a constant. And that's nice. That's what we want when we're trying to describe regions that we're integrating over. If we're trying to make them into boxes or rectangular boxes, that is our variable between two constants, we have to identify what kind of objects are made with taking our variable and setting it equal to a constant. And in this case, with spherical coordinates, setting rho equal to a constant makes a sphere. So spheres are very natural objects to describe in spherical coordinates. That's really why we're calling this spherical coordinates, because they are one of the most natural objects to describe using these coordinates. So let's look at the next example. Identify these surfaces. So r is equal to 4 sine theta. So what is that? Well, this is telling us that we've got a cylindrical coordinates description. And so since the z value is missing, this is a cylinder in cylindrical coordinates. So we'll first sketch what it looks like in the plane. And so this is going to be a circle that's centered at 2 and has a radius of 2. So let's label it as r equals 4 sine theta. And that means, so this was our y-axis, and this is our x-axis. So that means when I sketch it in three-dimensional space, and we'll just label these axes as the rectangular coordinate axes, then what it is it's a cylinder. Maybe I'll change the color of it here. So it's a cylinder that's opening up. Something like this. And so this is our cylinder. R is equal to 4 sine theta. Now you may say, how did I know that it was a circle that was shifted up 2 units of radius 2? So one way is that we've worked with polar coordinates in previous classes, and we can identify these kinds of curves as giving us these certain shapes. So circles are defined by equations like this in polar coordinates, at least circles that have been shifted away from being centered at the origin. However, another way we could see that is to just take the equation itself and let's multiply through by r. The reason I'm multiplying through by r is because I'm going to try to put this equation into an equation involving x's and y's and z's. Here, r squared is x squared plus y squared, and r sine theta is y. So this becomes x squared plus y squared minus 4y is equal to 0, or x squared plus y minus 2 squared is equal to, so when I completed the square here, I've got a y squared, I've got a minus 2 times plus a minus 2y, so a minus 4y, and then I've got this extra 4 I added on over here, so I've got a 4 over here as well. And this is that circle that we just wrote down, shifted up 2 units of radius 2. And so what we've done is we've identified the surface. It is a circular cylinder. Okay, what about the next one? I'll put a divider line here. That next surface, B. So this one's in spherical coordinates because we can see the rho and the phi there. So this is spherical coordinates. And in this case, we get rho squared sine squared phi minus 4 cos squared phi is equal to 1. Now when I think back to the equations, I can even take a peek just above here because I've written them down here. There they are, the equations that relate x, y, and z to our spherical coordinates. I see that I can deal with a rho times a cosine, but a rho times a sine phi, I need those extra things involving the thetas there. So this gives me an indication that wherever I see this sine phi, I should switch it to cosine. So I'm going to write that sine squared as a 1 minus cos squared phi. And then we've got that other minus cos squared, or 4 cos squared phi. And this becomes a 1 minus 5 cos squared phi is equal to 1. If I multiply through by rho squared, I get this expression. And rho squared is x squared plus y squared plus z squared. And then we got a minus 5 z all squared is equal to 1, or x squared plus y squared minus 4z squared is equal to 1. So there is our rectangular coordinates equation for this surface, and this is a hyperboloid of one sheet. So it's going to look something like this. I'll just draw a quick sketch of it down below. We've got our axes here, and our object is looking like a hyperboloid of one sheet opening along the z-axis. So it's going to look something like this. Right, we get this from our traces. When I take z to be some k value, this is really the equation x squared plus y squared equal to 1 plus 4k squared. So the radius is increasing of our circle. The farther up we go, or further down we go, the z-axis. So they're increasing circles as we go up and down the axes. They're smallest right around the origin, so in the xy plane. Now we'll get some examples in where we look at regions defined by inequalities. So this first one, theta is trapped between 0 and pi by 2, and z is trapped between r and 2. So this is in terms of cylindrical coordinates. We've got that theta is trapped between 0 and 2 pi, so that means our theta value is going to range over these values here. Z is trapped between r and 2. What is z equals r? Well, that's a cone, right? Because r is the square root of x squared plus y squared. So this is really z is equal to the square root of x squared plus y squared, or it's a cone. And so what we have is that our z value can go all the way up to 2. So we'll put a couple of reference lines in there. And it's got to be trapped below by the cone. So we've got a cone here. It's going to look something like this. It's like a quarter of a cone. Got these lines coming down here to make up that cone. And we've got our theta value. And what about our phi value? There's no restriction on our phi value. So this is our solid. This is our solid cone. So this is a solid quarter of a cone. And what's our next example? So this is spherical coordinates. Phi is between 0 and pi by 3. So again, remember with phi, we imagine we're at the z-axis. Phi is just that drop that we come down in any direction. The direction really depends on the theta value, but phi is just that drop. Phi is allowed to drop down to pi by 3. So maybe I'll draw one of them in here, pi by 3. And so we've got this, that alone, so phi is equal to pi by 3, that's a cone. It's everything inside of this cone. And then rho is also allowed to sweep out all values from 0 out to 2. So we're going to go all the way out here to a distance of 2. But then also for the smaller phi values, we're allowed to go to a distance of 2. So we've actually got this spherical cap on here. This sphere of radius 2, that's sort of a poor job of drawing it, but a sphere of radius 2 that sort of looks like this, but we're only interested in the upper cap. So it looks like this. And that's our rho is equal to 2, spherical cap. And so our region is all the stuff trapped inside these two surfaces. So this is like, I don't know what we'll call it. Maybe we'll call it like an ice cream cone. It's got the cone itself and then the scoop of ice cream on top included in it. So let's now have a look at the next example. We've got a description about this solid. It lies above this cone. Z equals square root of x squared plus y squared. And below this sphere. So let's make a note of these things. We've got our cone. Z is equal to square root of x squared plus y squared. We've got our sphere. X squared plus y squared plus z squared is equal to z. So that's not a sphere I can readily draw because it needs to have its z variable, that completing the square there. So I'm going to write this as a z squared minus z is equal to 0. If we complete the square of that, we get z minus 1/2 all squared and that gives me the z squared minus z, but it also gives me an extra quarter on that side, so it's got to balance by putting a quarter over here. So that's a sphere moved up a half and of radius a half. So what's our cone? Our cone is going to look like this. And it goes on, eventually it goes on indefinitely, but we're going to hit the sphere at some point, so I'll just stop drawing it. And then at this point we're going to hit a sphere. So we hit the sphere, and the sphere is going to go up from there. So we got our sphere that's looking something like this. I kind of need to know where I'm hitting the sphere. Am I hitting it below its center point, below its equator, above its equator? So I'm just going to leave that drawing off for just a second, and I'm going to look for the intersection. So what is our intersection? So our intersection is, for our sphere, we've got x squared plus y squared plus z squared is equal to z. But x squared plus y squared is equal to z squared because that's our equation of our cone. So I get z squared plus z squared is equal to z, or I get 2z squared is equal to z, or I get z is equal to 1/2. So they intersect at a height of z equals 1/2, and that's going to be the center of the sphere because it got moved up to z equals 1/2. So we've got our sphere that's sort of sitting right up here. So there's our sphere. And our radius of our sphere is 1/2 as well. So, if I was to draw the rest of the sphere in, sort of a poor drawing of the sphere, but it would look something like this. It goes right through the origin and then it wraps around up top. So there's our full sphere, but I'll get rid of those things and just leave the portion that sits above the cone. So there's what we have. We've got our sphere, x squared plus y squared plus z squared is equal to z, and we've got our cone, z is equal to the square root of x squared plus y squared. But we're interested in writing them in terms of inequalities involving spherical coordinates. So let's go ahead and do that. When I write the cone in terms of spherical coordinates, what is that? Well, cones are surfaces that are defined by phi is equal to a constant. So this would just be phi is equal to pi by 4. What about the sphere? Well, in terms of spherical coordinates, the first equation, as we've written the sphere, the left side would be rho squared, the right side would be rho cos phi, and so we could cancel out a rho and get rho is equal to cos phi. So there is our sphere in spherical coordinates. There is our cone in spherical coordinates. And so that means our inequalities that describe the solid are the following. Theta can be anything. It can go from 0 to 2 pi. Phi can go from 0 to pi by 4, and rho can go from 0 all the way out to cos phi. So there's our inequalities. So that means if I was to integrate over a region like this, in rectangular coordinates I'd have to use all of those expressions involving square roots and the like, but in terms of spherical coordinates, I've got theta and phi are trapped between two constants, and rho is just trapped between 0 and a cosine. Alright, so that's it for this first part of the video where we just introduced the coordinate system, how to take points in one coordinate system, rectangular, translate them to spherical and back again, how to describe surfaces in spherical coordinates when they're given in rectangular coordinates or vice versa, and how to describe regions, so solids, in one coordinate system as compared to the other coordinate system. In the next part of this video, we'll introduce how to convert a triple integral from rectangular coordinates into spherical coordinates. And then we'll do an example where we actually do this conversion and integrate. And then the third part of the video is we'll just do another example of a solid, and try to decide whether it's best to do it in rectangular, cylindrical, or spherical coordinates. Alright, that's it for this first part. We'll see you in the next video.